back to educator.com and welcome back to linear algebra. Today's lesson we're going to be discussing linear transformations. So this is going to be the heart and soul of linear algebra, is this notion of a linear transformation, also called a linear mapping. More often than not, I will probably refer to it as a mapping instead of a transformation, simply because it's habitual for me to think of it as a mapping as opposed to a transformation. It is true that what you're doing is you're actually transforming something, but when we actually define what we mean by a mapping and get into it, it'll probably make more sense to call it a mapping, because we're actually taking something and literally mapping it onto something else. So let's go ahead and get started. This is probably, for those of you who are physicists, engineers, and also mathematicians, this is where it's going to be probably the first introduction to something that you haven't necessarily seen before, or something that you've seen before that's going to be discussed in a very, very different way, a very general way, a mathematical way, and in a more abstract way, if you will. So a lot of it may seem a little odd. However, just by diving in a little bit, taking a look at some of the examples and letting them wash over you a little bit, you'll realize that it's not altogether different than what you've already been accustomed to. It's just looking at it from a different angle, from a more general angle. And again, that's what we do in mathematics. We take something and we try to generalize it as much as we can, to take that generalization, that process of abstraction, as far as we can. Okay, let's go ahead and get started. So this is an introduction to linear transformation, an introduction to linear maps. The first thing that we want to do is generalize this notion of a function that you've been dealing with for years now. So we want to generalize that notion, and that's what it is that we're going to be calling a map. So let's start with something that we do know. Let's take the function f of x equals x squared. Now let's talk about what this means and what it is you're actually doing here. It's saying, take a number x from the real number system, do something to it, in this case square it, and then you're going to get back another number. So you're starting someplace, you have an input, this x value, you're doing something to it, that is your function, and then you're going to end up with something else. So in this case, if I take a 2, I end up with a 4. If I take a 3, I end up with a 9. If I take a 4, I end up with a 16. You know how to deal with this. You've been dealing with it for years now. Okay, let's represent this in a slightly different way. I'm going to draw a couple of pictures here. Okay, and I'm going to say this is my space of real numbers. You're used to thinking of real numbers as a real number line. That's fine. This is just another way of representing it as a set, as just a collection, a bag of numbers, if you will. So, and I call it R, because it's the real numbers. And I'm going to sort of duplicate that over here. Now I'm going to show you what it is that's actually going on. Let me pick a couple of numbers from the real numbers. Let's say 2, 4, and 6. Here's what this function is doing. You're taking a number from the reals, the set of real numbers. You're performing an operation on it, this so-called f, which is defined by this, okay? And you're getting back another number, 4. You're taking a 4 and you're coming over here, you're squaring it, you're getting a 16. You're taking a 6 and you're coming over here, you're getting a 36. So as it turns out, what you're doing is you're mapping 2 to 4, you're mapping 4 to 16, and you're mapping 6 to 36, and so on. In other words, to every number in the set of real numbers, you're associating another number in the set of real numbers. So you've taken something from the reals and you've ended up back in the reals. You can think of it as sort of ending up back in the same set, but we like to represent it this way. We like to think of them as two different sets. And we actually denote this like this. We say f is a mapping from the real numbers to the real numbers defined by f of x equals x squared. So this new symbolism is the symbolism that we're going to be using. This sort of implies that. You know what's going on, but now we're sort of breaking it down to say what it is that we're really doing. We're taking one number, we're fiddling with it, and we're spitting out another number, something from. So we actually treat these two spaces as separate. In fact, we call this the departure space. Not everyone refers to it like this, but I think it's the best way to refer to it. And this is the arrival space. In other words, you're taking a number from the departure space, you're leaving that space, you're doing something to it, performing, operating on it, whatever it is you want to call it, performing a function, and then you're arriving at some other number, some other place, the arrival space. Now in this case, you're starting with a number and you're ending with a number, but that doesn't mean you always have to do that. As it turns out, in a minute you'll see we can start with a number and end with a vector. We can start with a vector and end with a number. Or we can get even more bizarre. We can start with one mathematical structure and end up with another mathematical structure. That's why this representation is the most general. So again, f is a function, is a mapping from R to R. What this means is that I pick a number from the real numbers, I do something to it, and I end up in the real numbers. That's what this symbol represents. And defined by, I actually give the definition of what the function is, what it is that I'm doing, what operation I'm performing. In this case, I'm actually squaring a number. Let's do another example. Let's say I have the function f of xy. Now I have two variables, is equal to x squared plus y squared. Let's just do a simple example. If I take the point 1, 2, okay, it's x squared plus y squared, so 1 squared plus 2 squared is equal to 1 plus 4, that's equal to 5. Now you've probably never even thought about this before, but take a look at what's going on. Now I'm taking two numbers from R, and the way this is represented, notice this is actually a vector representation. When I have two numbers like this, a point in 2 space, which is what this is, the point 1, 2, is also a vector in 2 space. So we represent that, of course, with R2. So when I symbolize this, according to how we did it here, here is what I'm writing. The function is a mapping from R2 to R, defined by f of xy equals x squared plus y squared. I could also write this in vector form. The f of xy, the vector xy equals x squared plus y squared. And again, this coordinate xy is the same as a 2 vector. So what this symbolism means is that my departure space, if you will, is now R2. It's the space of 2 vectors. My arrival space is R, the set of real numbers. I've taken a vector. I've done something to the individual components of that vector, and I spit out a number. So these are two different spaces. Even though I'm picking numbers, all the numbers are from the real number line, we actually consider this thing that we take, this vector that we take, as a single unit. So I took a 2 vector, I did something to the components of that 2 vector, and I spit out a number. That's what this symbolism means. That's why this is a very powerful symbolism, and it generalizes. This is a mapping from R2 to R. That means to the space of 2 vectors, I'm associating a number. To the space of to every element in the space of 2 vectors, I'm associating a number. I'm mapping a vector to a number. I'm mapping a 2 vector to a number. That's what's going on here. Let's do something like this. Let's define f of x, y, z is equal to x plus y, x plus z. Let's do an example to show what this actually looks like. If I take f of 3, 2, 1, well, this is telling me x, y, z. This is a 3 vector. In other words, it is a vector in 3 space. If I take this, the answer that I get is, well, x, the first component is x plus y, so 3 plus 2 is 5, and x plus z, 3 plus 1 is 4. I've taken a 3 vector, I've done something to it according to the definition of the function here, and I've spit out a 2 vector. So this is represented this way, pictorially. This is R3. It's the space, the collection, the set of all 3 vectors. 569, 246, 135, 009. A set of 3 vectors. And here is my set of 2 vectors, R2. I'm taking something from here, I'm doing something to it, and I'm ending up in a completely different space. I'm mapping it from one space to another space. This, according to the symbolism, is written like this. F is a mapping from R3 to R2, defined by f of, I'm going to write it in vector form, x, y, z is equal to x plus y, x plus z. This tells me that I'm taking a 3 vector, I'm performing an operation on it, this operation specifically, and I'm ending up with a 2 vector. That's kind of extraordinary when you think about it. You've been doing this all along, actually. It's not the first time you've seen this, but to actually step back and realize that you're jumping from space to space, that's pretty extraordinary. And in a minute, when we define what we mean by a linear mapping, it's going to be even more extraordinary that you can actually retain structure when you jump from one space to another space. Okay, let's do another example. This time we'll do f of xy, and we'll define it as x squared, the second one as y squared, x plus y, x squared plus y squared. In this case, let's do an example, f of 2, 3. Well, x squared is 2 squared, that's 4. Second is y squared, that's 9. X plus y is 2 plus 3, that's 5. X squared plus y squared is 9 plus 4, that's 13. So f of 2, 3 equals 4, 9, 5, 13. I've taken a 2 vector and I've spit out a 4 vector. I've went from 2 space to 4 space. I went from R2 to R4. Another way of representing this is I have mapped 2, 3 to the vector 4, 9, 5, 13. Just like in the previous example, I've mapped one vector to another vector. Each vector belongs to a different space. That's why the symbolism actually is more general and works out beautifully. And it is a mapping from R2, a 2 vector, to R3, no, not R3, R4. Defined by this, defined by f of xy equals x squared, y squared, x plus y, x squared plus y squared. To each vector in 2 space, I'm associating a vector in 4 space. The picture looks like this. The set of all 2 vectors, this is R2. Here is the set of all 4 vectors, R4. That's what's happening. I treat them as separate spaces. That's what makes this beautiful. I'm moving from one space to another. I can do whatever I want to something that I pull from my first space, and then I end up somewhere else. It's really very, very extraordinary that you can do this. And it's even more extraordinary that we can actually represent the real world as operating like this. Okay. So this is called a mapping, again. Now, what we're concerned with are linear mappings because we're dealing with linear algebra. So now we're going to actually give a definition of what we mean by linear. The examples that we gave a second ago, they're just standard mappings. As it turns out, in all the possible mappings, there is a small portion of them that are actually linear and they have special properties. So now we're going to define what we mean by a linear mapping. And anytime we're faced with a mapping, we want to check that it's linear, we're going to check this definition. We'll do that in a second. Okay, very, very important definition, probably the single most important actual definition in linear algebra. Definition, okay. mapping, or a mapping, sorry, a mapping from Rn to Rm. Let me make this a little bit better here. To Rm, where n and m can be anything. 2 space to 6 space, 1 space to 1 space, 3 space to 3 space. It's more general now. A mapping from Rn to Rm is an operation which to each vector in Rn, our departure space, assigns a unique vector symbolized Lu in Rm. Don't worry about what this, it'll make sense in a minute when we actually start doing the examples. I'll discuss what these symbols mean. Again, we just want the mathematical formalism so that our bases are covered, such that the following hold. Okay. A, L of u plus v equals L of u plus L of v, and B, L of c times u equals c times L of u. Okay, let me just talk about what this means real quickly and we'll get to the examples. So a mapping from the space Rn to the space Rm, or the mapping from n space to m space, is an operation which to each vector in Rn, okay, associates a unique vector that is symbolized that way to Rm, such that the following hold. Notice I haven't drawn any pictures yet. I will draw pictures in a minute, but it's very important to understand that these are algebraic properties. So we're talking about a linear mapping, and yet we've drawn no lines. We've drawn nothing else. This is an algebraic property. So the following has to hold. I have to check these two things when I'm presented with a mapping. It says, if I map u to its whatever I'm associating with it, and if I map v to whatever I'm associating with it, and then I add those, it's the same as if I add them first and then perform the operation on it. So in either order. That's what this says. That's what linear means. It means I can either add the two elements from my departure space and then operate on it, or I can operate on it and then add them. But in either case, they have to end up in the same place. And the same thing here. If I start with a vector in my departure space, multiply it by some scalar, and then operate on it, meaning my function, whatever my function happens to be, it's the same as operating on the vector first and then multiplying it by its scalar. This might seem obvious. You're going to discover in a minute it's not so obvious. Okay, let's draw a picture and show what this means exactly. So we have our departure space, we have our arrival space, and again, we're considering these spaces as collections of 2 vectors, 3 vectors, whatever. So this is going to be Rn, n space, Rm, so they're totally different spaces. They don't have to be, but often they are. Let's say I have u, and let's say I have v, and let's say I have u plus v, which I can do, right? If I have 2 vectors, I can just add them and I get another vector because vector addition is closed. I end up in the same space. Over here, let's say I operate on u, and I end up with Lu. Let's say I operate on v, I have Lv. Well, these are just vectors in m space. I can add vectors in m space, and I get a vector in m space. So this is another Lu plus L of v. Here's what linear mapping says. It says that if I take u and v And if I do u first, and then if I operate on v separately, and then over here, if I add them, I'll end up here. And then if I do it the other way, if I add them first to come here, and then I operate on them, it says I have to end up in the same place with the same answer. Think about what that means. So let me say that again. This is really, really important distinction. If I have a mapping like x squared, well, this says that if I do x squared, and then if I do y squared, so x squared gives me over here, another x squared gives me over here, well, if I add the x squared plus y squared, I'm going to get some number. Now, if I do it the other way around, if I add my x and y first before I square them, if I take x plus y, square it, and then I do my operation, so if I reverse the order, it tells me that if I end up in the same place, my mapping is linear. If I don't end up in the same place, my mapping is not linear. So that's what linear means. It means I can do my function or my addition in either order. I still have to end up in the same place. That's what's important. And we'll see in a minute that that's not always the case, that linear mappings are very, very special things. And the same thing with, of course, the scalar multiplication. I have u, I can end up, if I can multiply it by some scalar first and then operate on it, or I can operate on it and then multiply it by a scalar. I'll end up in the same place. I should end up in the same place. So this is what I have to check every time I'm faced with a mapping. I have to actually put each value in there and manually check it. You have to go through the rigorous process of actually checking to see that a mapping is linear. Later, of course, we'll come up with quicker ways, but for the time being, we want to get a feel for what linear mappings are. Okay. I cannot emphasize enough how profoundly important this definition is. It is very, very, very important, this notion. Spend some time with this idea. And again, operate first and then add, or add first, then operate. In either way, you have to end up in the same place. If you end up in the same place, it's a linear mapping. If you don't, it's not a linear mapping. Okay, examples will always clear up everything. Let's do our first example, which we talked about. Let's say, and I'm going to use the symbolism that I've used before, f is a mapping from R to R. So I'm starting with a number, I'm spitting out a number, defined by f of x equals x squared. So you're very familiar with this function, been dealing with it for years. We want to know, is it linear? You might already know the answer to this, but let's actually go through the definition, and then we'll talk about what linearity really means. Okay, well, we have to check the two properties that we talked about. We have to check that vector addition is linear and scalar multiplication is linear, that it satisfies those two properties from before. Okay, let's do part A. We need f of x1 plus x2 to actually be equal to f of x1 plus f of x2. It means we add the two x's first and then operate on it. It has to be the same as operating on each separately, then adding them. Okay, that's what this means. That's why the parentheses are arranged the way they are. So let's check that this is the case. Let's do this one first. Let's move on to a blue ink here. So I'll do f of x1 plus x2. Well, the definition of the function is you square it. That's equal to x1 plus x2 squared. That's what this parentheses means. Anything in the parentheses, that's what you do to it. Well, that equals x1 squared plus 2x1 x2 plus x2 squared. So that takes care of that. Now let's do f of x1, f of x2. f of x1 is equal to, well, x1 squared. That's the definition of our function right here. So all we're doing is we're using the definition of the function, putting in the values, seeing what we get. f of x2 equals x2 squared. So we have f of x1 plus x2. We calculated it. That's here. Here. We have f of x1, that's here. We have f of x2. Now let's see if they're actually equal. Now let's check this thing. x1 squared plus 2x1 x2 plus x2 squared. The question is it equal to f of x1, which is x1 squared, plus f of x2, which is x2 squared? Are these two equal? No, they're not. This is an extra term. They are not equal. Therefore, we don't even have to bother checking the scalar multiplication. This is not linear. It's not a linear mapping. It is a mapping from R to R. Yes, of course it's a mapping. In fact, it's a specific type of mapping called a function. But again, we don't want to use the word function again. We want to use the word mapping or transformation. It is a mapping. It's a perfectly valid mapping. It's a very common mapping. It shows up everywhere in math and science, but it's not a linear mapping. Okay. Let's try another one. Let's see, let's go back to our black ink here. Let f be a mapping again from R to R, from the real numbers to the real numbers, meaning we start with a real number, we fiddle with it, and we get a real number back, be defined by f of x is equal to 5x. Okay. We need to check that f of x1 plus x2 equals f of x1 plus f of x2. Okay, let's do that. Let me actually work in red. So there we go. We go to red. Oh, f of x1 plus x2. Well, here's our definition of our function. This is what it's 5 times the thing in parentheses. So it's 5 times x1 plus x2 equals 5x1 plus 5x2, distributive property. Well, now let's do f of x1 is equal to 5x1. F of x2 equals 5x2. And now let's check to see if they are equal. We need to check that. F of x1 plus x2 equals, let's use a blue ink for this one, 5x1 plus 5x2. The question is, does it equal f of x1 plus f of x2? 5x1 plus 5x2. Yes, it checks out. The left-hand side and the right-hand side are the same. Adding them together first, then operating on it, versus operating on each and then adding it, they end up being the same. So far, so good. Now we want to check scalar multiplication. So f of cx equals, we want to check to see whether it equals c times f of x. Well, f of cx, this is our 5cx, and c times f of x, so we're checking this one, equals c times 5x. Well, 5cx does equal c5x, so B checks out, scalar multiplication. So yes, this is a linear mapping. Okay, this is a really important example. Look at this, y equals 5x. You know that f of x equals 5x if I write it as y equals 5x. This is the equation of a line. That's where we get the name linear mapping. But, and this is why you know that anytime you see an exponent of 1, you're talking about a line, a linear function. Now you know why we call it a linear function. However, it's really, really important to understand that linearity is an algebraic property, not a geometric property. Geometry and pictures are just there to help us out. We get the language that we use. For example, we call it a linear mapping because we think of it as a line. But believe it or not, just because we can draw something doesn't necessarily mean that there is such a thing as a line. This is an algebraic property. It's a deeper, more mathematical property that has to do with mappings, of moving something from one space to another. That's why it's called linear. We, of course, do it the other way. We study lines. We know that lines are equations where the exponent on the x is 1. But this is what's going on. Now you understand something very, very real and very deep about mathematics. This is an algebraic property. Pictures are not proofs. They can help. Okay. Let's see what we've got. Let's go back to, let's stick with blue. Okay, now let's do L, we can call it any letter we want, as a mapping from R3 to R2, defined by L of x, y, z equals x, y. This says that if I have a 3 vector, I start with a 3 vector, I operate on it, I get a 2 vector, and the operation that I'm performing is just take the first component, take the second component, drop the third component. So I'm converting, transforming a 3 vector to a 2 vector. I'm mapping from the R3 space to R2 space. Question is it linear? Well, let's check. We have to pick a u and a v, so we'll let u be the vector u1, u2, u3. It's really, really important to keep track of all of your indices, all of your subscripts. There's a lot of notational intensity going on. There's nothing particularly difficult, it's just standard arithmetic, but it's true. This does tend to get a little notationally intensive, notationally busy, rather. So be very, very careful. I mean, I'm going to make mistakes, believe me. Equals v1, v2, v3. Okay, let's calculate L of u plus v. Well, L of u plus v, well, that means this is a parenthesis, so let's do u, that's L of, that means add them first. Well, that's just u1 plus v1, right? We're adding components. u2 plus v2, u3 plus v3. Now we can apply L to this one vector this way. That's equal to, just take the first component, u1 plus v1, u2 plus v2. So that's the first thing that we have. Now let's take L of u. Well, that's just equal to u1, u2, and let's take the L of v, which based on this definition is just the first component, the second component, right? And now let's see if these two actually equal each other. So the question is, does L of u plus v, does it equal L of u plus L of v? Well, L of u plus v equals this thing that we got before, u1 plus v1, u2 plus v2. Does it equal L of u, which is u1, u2, plus this one, v1, v2? Well, when we can perform this addition. Again, we have to go as far as we can with the actual arithmetic. That equals, this is a 2 by 1 plus a 2 by 1, so we add components. u1 plus v1, u2 plus v2. The question is yes, they are. So the first part checks out. We still have to check scalar multiplication, so let's go ahead and do that. Let me move on to the next page. Okay, so we have to check that L of CU, does it equal C times L of U? Well, let's do L of CU. L of C times U equals L of CU1, CU2, CU3. That's equal to, we just take the first two entries, CU1, CU2, right? And then we'll calculate this other one. C times L of U equals C times, well, the L of U is U1, U2. It's equal to, yeah, CU1, CU2. These, me and my arrows. These are definitely equal. So as it turns out, scalar multiplication also satisfies this equality, the definition, the second part of the definition of linearity. So yes. This is a linear mapping. Okay. This example that we just did is a very, very important mapping. Let me go back to black. This mapping is called the projection mapping. Remember we mentioned projection a little bit earlier, or the last lesson, I think? Projection mapping. In this particular case, L of x, y, z is x, y. This is a mapping from R3 into R2. All we've done is project onto the xy plane. We've taken a 3 vector, we've shined a light on it, and we have just taken the projection onto the xy plane. Let's draw this one more time. This is our right-hand coordinate system. We have the x-axis, we have the y-axis, and we have the z-axis. Let's take a vector, for example, 2, 3, 5. We project it onto the xy plane, which means we drop a perpendicular onto the xy plane. And this vector that we get, this 2 vector, because now we're only talking about 2 space. We're not dealing with the z. This is that. We've taken a 3 vector, we've projected onto the xy plane. In other words, we've eliminated the z component, and now we have this vector, which is in the xy plane. This is a 2 vector. This is really, I mean, when you think about it, it's kind of extraordinary. Something that seems so natural that we can actually do this. We can move from one space to another space, the space of 3 vectors to a space of 2 vectors. And not only that, that we can actually retain structure. And what that means is that if you add in one space and then operate, it's the same as operating and then adding in the second space. That's what you're doing. That's amazing that you can actually do that. That structure is maintained in moving from one space to another, when the 2 spaces really have nothing to do with each other. They're completely different. Okay, let us, just terminology here. So let's go back to our picture. We have our departure space, depart, arrive. Sorry about that, departure space, arrival space. We're taking something from element from here, we're operating it under some mapping, linear mapping in this case, and we're ending up with some other object over here. They could be 2 completely different spaces. If we call this U, and then of course we call this L of U, because we've operated on U, it's a different element now. Okay, this L of U, this thing right here, is called the image under L, the mapping, which makes sense. You're taking this, you're doing something to it, so this is the image under the mapping L of this original element. It's the unique element associated with this, the element from the departure space. Okay, the set of all images for a given set, or a given set of u's, is called, and you know this, you've seen it before, is called the range. In other words, if I have this set, let's say I only take 5 elements from that set, okay? 1, 2, 3, 4, 5. And let's say I'm only mapping those 5 elements. And I map over here to, let's symbolize what they look like, the images, like that. If I take the collection of these things in this space, that's what I call the range. The range is not the entire space, okay? It's very, very important to differentiate that. Sometimes it can be. Sometimes we'll map everything in one space over onto another space, and it might actually end up where everything here is associated with everything here, that there are no blanks, no gaps, but that's often not the case. The range, okay, the range is just those things that actually end up as images under the choices that we make from the departure space. The range is not the entire space. The range is just everything that happened to be mapped over here. 2, 3, 4, 5. In this case, the range consists of 5 elements, and what we might say is we usually talk about this as the domain, and this is why the whole domain range thing is actually not often used when you actually move on to speaking about linear mappings more generally. We still use the term range. We don't often really speak about the domain. So speak of the departure space, the arrival space, the individual element as an image, and the set of images for things that you do map is called the range. Okay, let's see here. What else have we got? Okay, let's do one more example. We will let a mapping L be a mapping from R3 to R2 again, defined by U1, U2, U3 is equal to U1 plus 1, U2 minus 3. So we're taking a 3 vector, mapping it to a 2 vector, and this is what we're doing to it. We're taking the first entry, adding 1 to it, and then we're taking the second and subtracting the third from it. Okay, so an example might be L of 3, 2, 2. That's going to equal 3 plus 1 is 4, 2 minus 2 is 0. Just an example of what that mapping looks like. Notice I've changed a 3 vector to a 2 vector. Okay, let's check our first one. We need to check L of U plus V. Okay, so L of U plus V is equal to L of U1, U2, U3 plus V1, V2, V3 equal to, we're in the parentheses still, so let's actually do it. L of U1 plus V1, U2 plus V2, U3 plus V3, and now I can apply L to this using this. That means I take the first entry and add 1 to it, so that's equal to U1 plus V1 plus 1, and then U2 plus V2 minus U3 plus V3. Take the second entry, subtract the third from it. So let me put a circle around this. This is what we have for that. Go back here. Now let's calculate L of U, which is equal to first entry plus 1. Oops, forgot my U. This is supposed to be a U3. It's to U1 plus 1, U2 minus U3. Okay. Then I'll do L of V. It's equal to V1 plus 1, V2 minus V3. Now I actually check that these are equal. Okay, let's see. So let me move forward. I am checking that L of, now I take L of u plus L of v. Let me calculate that because that's the right side of the thing that we're going to check. That's going to be u1 plus 1, u2 minus u3, plus u plus v. Let me make this clear. v1 plus 1, v2 minus v3 equal to u1 plus v1 plus 2 and u2 minus u3 plus v2 minus v3. Okay. When we did L of u plus v, back that thing that I circled, we ended up with u1 plus v1 plus 1 and u2 minus u3 plus v2 minus v3. No, I'm sorry, that's not right. Like I said, mistakes are easy. u2 plus v2 minus u3 plus v3. We got this. The question is it equal to the thing that we just got, which is L of u plus L of v? Well, is it equal to u1 plus v1 plus 2 and u2 plus v2? I'm going to rewrite this so that it actually looks minus u3 plus v3. So notice this matches that. That's fine. However, this is not the same as this. When we wrote it all out, we ended up with two things that are not equal. So this particular mapping is not linear. So when we're given a mapping, we have to use examples, general examples, u and v. We have to check that adding those two vectors then operating on it is equal to operating on those two vectors separately and then adding them. If those two are equal, that's half of it. Then we have to check to see whether take just any old vector, multiply it by a scalar, then operate on it. If it's the same as operating on the vector and then multiplying it by a scalar. If it ends up in the same place, the mapping is linear. That's the definition of a linear mapping. It has to satisfy those two properties. That operation and addition, operation and multiplication, you can reverse the order. You still end up with the same place in your arrival space. If you end up in different places, the mapping is not linear. Profoundly important definition. And we're going to spend the rest of this the rest of the semester, the rest of all the lessons, discussing everything that this ultimately implies. Thank you for joining us today at educator.com for linear algebra. We'll see you next time.